We've discussed empirical and molecular formulas in previous lessons, but in this lesson specifically, I'm going to explain how you can actually determine the empirical formula and the molecular formula from data that's provided to you. So let's start off really quickly reviewing what an empirical formula is. Remember that an empirical formula is the relative number of atoms of each element in a substance. So for example, water. In water, H2O, you have 2 atoms of hydrogen for every 1 atom of oxygen. So that's the empirical formula. There's your example for water. Now, as an example, I'm going to show you how to calculate the empirical formula when you're just given percents of each atom in a compound. So in this problem, it tells you that you have a compound that's made up of carbon, hydrogen, and oxygen, and it tells you that 9.1% of it is hydrogen and 54.5% of it is carbon. So the first thing you should be asking is what percent of it is oxygen. So if 9.1% of it is hydrogen and 54.5% of it is carbon, the rest is going to be oxygen. So if I take 100 and subtract those two values from it, what I get is 36.4% being oxygen. Now, while the subscripts for your empirical formula represent the relative number of atoms, they also represent the relative number of moles, since there are always 6.02 times 10 to the 23rd atoms in a mole. So if, for example, I have H2O, I do have 2 atoms of hydrogen for every atom of oxygen. I also have 2 moles of hydrogen for every mole of oxygen. And so we're going to take advantage of that fact in calculating our empirical formula, because what we're going to do is we're going to take these 3 values and we're going to figure out how many moles they represent, and those moles, those relative moles, will become the subscripts for our empirical formula. Now, before we get started, we have percents here, and in order to get rid of these percents, what we can assume is that the total mass of our compound is 100 grams. If that's the case, then 9.1% of that 100 grams would be 9.1 grams. 54.5% of that would be 54.5 grams of carbon. And then finally, 36.4% would be 36.4 grams of oxygen. So now what we need to do is we need to convert each of these grams into moles, and I do that by using my molar mass. I put 1 mole up top, I put grams on bottom. The molar mass of hydrogen is 1.008, and when I divide 9.1 by 1.008, I get 9.278 moles. And notice I rounded to 4 decimal places. The reason why I round to 4 decimal places is because if you round too much, you'll see that you actually will have issues finding the correct empirical formula, and you'll see that in just a second. So make sure you round to 4 decimal places at least. All right, I'm going to convert this to moles as well. Now the molar mass of carbon is 12.01, and so when I divide, what I get is 4.5379, and my units are moles again. Finally, when I do this with oxygen, 1 mole and what I get is 2.275. 275. I didn't round this at all, so that's why I only have 3 decimal places. Now, I've got these 3 numbers. What I would love to do would be just to round them to a whole number, make them my subscripts, and then I would be done with this problem. However, you can't do that. You can't round this 4.5 to 5 because you have to be within 1/10 of a whole number. This 2.2, I cannot round that to a whole number. So instead, what I do first, before I start thinking about rounding, I'm going to divide all of these by my smallest number of moles. So the smallest number of moles in this case is 2.275. This helps me in order to get a whole number for my subscripts, as you will see in just one second. So when I divide 9.0278 by my smallest number of moles, I get 3.968. Now, 3.9 is within 1/10 of a whole number, which is 4. So I'm going to put 4 right there. I can round that. 4.5 divided by my smallest number of moles gives me 1.99, which is 2. I can round that. And this is going to be 1. So my empirical formula is going to be carbon first. So there are 2 carbons. So I'm going to write C2. Then there are 4 hydrogens, H4, and then oxygen. So this is the formula, C2H4O. Keep in mind a couple of rules that you need to remember. The first is that you need to carry decimal places out at least 4 digits when you're doing your calculations, like I explained when I did my calculations. Second, you can only round to a whole number if it's within 1/10 of that number. So for example, 1.03, I can round that to 1. If I had 1.3, however, I could not simply round that to 1, and that brings you to the third point. If you are not within 1/10, you'll need to multiply all of your answers so that they are whole numbers. So for example, if you have 1.5, you cannot round that to 2. You must multiply all of your subscripts by 2 to get 3. In my example before, if you have 1.3, you can multiply 1.3 by 3 and you'll get 3.9, and you can round that to 4. So keep in mind, if you're not within 1/10 of a digit, you have to multiply all of the subscripts by an integer to make sure that you get whole numbers. So far, you have learned how to calculate the empirical formula based on analytical data that is given to you. So in the previous example, you discovered that the empirical formula for that compound is C2H4O. Now we're going to take that information and we're going to learn how to convert from an empirical formula into a molecular formula, which is the formula that you would see in a lab. So to calculate from an empirical formula to a molecular formula, the first thing that you need to find is a whole number multiplier. So this whole number multiplier is simply the molecular mass, which is the molar mass of the molecular formula. Now, since we don't know the chemical formula for the molecular formula, that would have to be given to us, which it is in this problem. It's 176 grams per mole. That divided by the empirical molecular mass, so the empirical mass. That will give us a whole number. So let's actually calculate that right now. The molecular mass is given to us as 176 grams per mole. Now I need to find the empirical mass of my empirical formula, which is C2H4O. So I take 12.01 times 2 plus 1.008 times 4 plus 16, and what I get is 44.052 grams per mole. And when I divide that, I get 3.995. That will round to a whole number of 4. So I've now calculated my multiplier. Now, well, what do I do with my multiplier? What you do with your multiplier is you take this multiplier and multiply every single subscript in your empirical formula by that value. So in this case, it becomes C8, H16, and then O4. This right here is my molecular formula. And the reason why I know it's my molecular formula is that I can reduce it. If I were to then divide by 4 again, I would get my simplest whole number formula, which is my empirical formula. So notice it's actually quite easy to convert from empirical formula to molecular formula. You just have to find this whole number multiplier and then multiply your empirical formula by that to get your molecular formula. There's another method in determining empirical formula, and that's by combustion analysis. Keep in mind that a combustion reaction involves the reaction of a hydrocarbon with oxygen, and what's produced is water and carbon dioxide. So this problem tells you that you have 0.255 grams of your compound, and it also tells you that 0.561 grams of carbon dioxide and 0.306 grams of water have been collected. So what we can do is we can use the mass of carbon dioxide in order to calculate the mass of carbon from the original sample, and we can use the amount of water that's being produced to calculate the amount of hydrogen, the mass of hydrogen in that compound. And this entire problem relies on the concept of the law of conservation of matter. Specifically, all of the carbon that's in carbon dioxide came from the hydrocarbon, and all of the hydrogen that is in water came from the hydrocarbon as well. Now, the only tricky part is figuring out how much oxygen was involved. And the reason why is because oxygen is split apart into its role in carbon dioxide and in water. So what I'm first going to calculate is the amount of carbon and the amount of hydrogen, the number of grams that the compounds that the hydrocarbon originally had. So in this problem, I'm going to start off and I'm going to work with carbon first. So I have 0.561 grams of carbon dioxide. Now I'm going to convert this into grams of just carbon. So in order to do that, I first need to get into moles of carbon dioxide in order to then convert into moles of just carbon. So I'm going to put 1 mole of carbon dioxide up top, which means I need to put the molar mass of carbon dioxide on bottom, which is 44.01 grams. Now I'm going to get into moles of carbon. So for every 1 mole of carbon dioxide, if you notice, there's no subscript here, which means there is 1 mole of carbon. And now I can convert into grams of carbon by putting 1 mole of carbon on bottom, and then the molar mass of carbon up top, which is 12.01. And when I do the math, I get 0.1531 grams of carbon. For the next problem, I'm going to figure out how much hydrogen came from the hydrocarbon. So I have 0.306 grams of water, and I need to convert that into grams of just hydrogen. So I'm going to put the molar mass of water on bottom, which is 18.016 grams on bottom. I'm going to put 1 mole of water up top. Okay. For every 1 mole of water, there are 2 moles of hydrogen because there's a subscript 2 in water. Now I need to convert into grams of into grams of hydrogen. So I have the molar mass of hydrogen, which is 1.008 grams, and 1 mole of hydrogen. And so what I end up with here is 0.0342 grams of hydrogen. Now, if the hydrocarbon had this amount of carbon and this amount of hydrogen and had a total mass of 0.255 grams, I can then calculate the mass of oxygen by subtracting. And so what I'm going to do right here is I'm going to write out the amount of each element that I have. So for this problem, I have 0.0677 grams of oxygen. I have 0.1531 grams of carbon, and I have 0.0342 grams of hydrogen. Now, in order to calculate the empirical formula, I now have to convert each of these into moles. Keep in mind, the purpose of all of this up top was simply to calculate what I had previously already known for other problems, the number of grams of each of the elements. So let's do that right now. It should actually be pretty quick at this point. So to convert from grams of oxygen into moles of oxygen, I need to use the molar mass, which is 16.00 grams. And when I divide, what I get is 0.0042. I have 4 decimal places out, moles. I'm going to keep going. I'm going to get into moles of carbon, so 12.01 grams. And what I get here when I divide is 0.0127 moles. And then finally, I get 0.0339 moles. Okay. Second to last step that I need to complete for finding the empirical formula, I need to divide by the smallest number of moles, which in this case is 0.0042. And what I end up getting up here, I get the whole number of 1. Here I get 3, and here I get 8. And so what that tells me is that the formula, the empirical formula for this is going to be C3H8O. So keep in mind, the only part of this entire problem that is new is this right here that is in black, and I'm starring right here. The purpose of that is to be able to calculate the number of grams of carbon and hydrogen based on how much carbon dioxide and water are produced, and then also to be able to calculate the amount of oxygen that the hydrocarbon started with based on the law of conservation of matter.